So this was just the summary that we learned last time, how to normalize a vector, right? We also talked about the Pauli spin matrices, right? It would be good to memorize them because this is the foundation for quantum mechanics and also quantum computing. And sigma z is 1, 0, 0, -1, right? Sigma, this one, we memorize it by realizing the eigenvalue are 1 and -1 for this matrix. So it's easy to memorize 1 and -1 along the diagonal. And then for sigma x, it's just off diagonal and it's 1, 1, right? And then y, you think you should realize that complex number should play an important role, and it happened in sigma y, right? And so it's I in this direction, but -I. Some people say negative is small number, so it floats to the top, right? So you find a way to memorize it, okay? They are anti-commute. They have this equation. Now, do you need to memorize this equation? You don't have to. Maybe you can put in cheat sheet. But more importantly is you need to understand this type of equation. You will see that very often when you study quantum mechanics or quantum computing. Right? What is the meaning of this? Now, if you see these curly braces, of course, it means it has a special meaning here, means anti-commute operation. What it means is the first one times the second one plus the second one times the first one, right? So in normal algebra, the number commute 2 times 3 equal to 3 times 2. So there's nothing special. But now we're talking about matrix. Matrix 1 times matrix 2 is not equal to matrix 2 times matrix 1. And among these Pauli matrices, they obey this law. Now then, what does this mean for ij? Ij is just an index, right? We say I can be equal to x, y, or z. You just plug in, okay? Or sometimes people call the Pauli matrix as sigma 1, sigma 2, sigma 3. And then the identity matrix is sigma 0. So just check carefully what they mean, okay? Now here I means x, y, or z. So sigma I, sigma j, just say that the first one has the index I, the second one has index j. But they can take any value, right? Not just I, j is also can be x, y, or z. You can take any combination of them, okay? So if they are different, for example, if it is I not equal to j, for example, you have sigma x and sigma y, then x is not y, right? Just treat x and y as a number. They are not the same, right? Then it's equal to 2 delta ij. So what is delta ij again? Do you remember? Canonical delta. What does it mean? It equals to what? Very good. Yeah. So he already memorized. I hope all of you memorize it. This is the foundation, right? You don't want to always check your cheat sheet, right? Be ready to do something more difficult and don't mess up. Okay. So this canonical delta, if they are the same, then it is 0, right? So if they are not the same, then it is 0, right? So what does it mean? For example, sigma x, sigma y plus sigma y, sigma x equals to what? It say equal to 2 delta xy times identity. Xy, although it is not a number, but what it's saying is that x not equal to y, right? The index are not the same. So as a result, this equals to 0. Any questions? Now you need to start practicing this. Get very familiar with this, comfortable with this. Okay. Don't get scared when you see this. Okay. Now then, we also talk about the adjoint matrix. I said I only want to spend 5 to 10 minutes, but I think it's good to just quickly review. A is a matrix. What is its adjoint? It's just a definition. Its adjoint, we put a dagger. This is like a plus dagger, right, on top of it. And what's the meaning of dagger? Again, this is definition. Memorize it, okay? It's the transpose followed by complex conjugate. Transpose of a matrix means the row becomes column, column becomes row, right? If A equal to A dagger, then it means it is self-adjoint, or it is called Hermitian, right? It's adjoint, or it is self-adjoint, or it is Hermitian, right? So every matrix, of course, has its adjoint matrix, right? Just like every human can find its image in the mirror. But is the image the same as who you are? Then depends. Some matrix, this is not a good analogy, but right, some matrix, they have their image equal to itself, the adjoint equal to itself. Then we say they're self-adjoint. Okay? And then I gave some example here, right? That follow this. Do not feel that you understand. Go back and try to follow one more time. The point is the devil's in the details. How do you do the transpose? How do you do the complex conjugate? And I show you that sigma y is Hermitian, right? By going through the process, first I take the transpose of this one. So row becomes column. First row becomes first column. So 0 negative I becomes negative 0 negative I vertically. And then I0 horizontally become I0 vertically in the second row. And then I need to take the complex conjugate. Again, complex conjugate change the imaginary part, not just of the number, right? Imaginary part of the number. So if there were a real part, the real part does not change, right? So that's why it becomes negative I becomes I, and then I becomes negative I. So you find that sigma y equals to sigma y dagger. So it is Hermitian. And this is very important because this related to the last slide that I want to spend time to talk about why we want Hermitian, right? So then, actually, also one more thing. This one I was not covered in the last lecture, so it's in the video I sent you, right? So I introduced more about the operation in bracket. Again, I do not think you need to memorize, but you need to understand, and actually nothing to memorize. Just ask you to find the image, right? The dual correspondence. You naturally will come up with the right format. Why? So if alpha is the cat, again, this is the vector, right? You find a corresponding vector in the bra space, right? They are correspondent, they are related. They are not equal to each other, they are related. And you remember in the matrix form, the bra is what? How do you find the bra in matrix form? Do you remember? Transpose and complex conjugate. Very similar to the adjoint matrix, right? Transpose and complex conjugate. So basically, if you are stuck with something, you forgot it, the only choice is transpose and complex conjugate. That probably is right, okay, if you are stuck, right? Now, X is a matrix. X times A is what? Times alpha. Is it a number, a matrix, or a vector? When you have an X times alpha. It's a vector. Why? The matrix sums of the vector. Yeah, very good. So a matrix times a vector, right? Now, sometimes it's good to think about matrix form, right? If you forgot about this, then you just think X times alpha. Okay, X is a matrix operator is given, right? You have many entries. And then vector is a column, right? So matrix times a column, of course, a vector, of course, still a vector, right? You just go through the multiplication. That's why if you forgot how to do matrix multiplication, just practice it. Don't let it drag you in this class, right? So it is still vector. So if this is a vector, then I must have a dual correspondence in the bra space, because we say every vector should have a dual correspondence, right? So basically this is like me, and then I raise my left hand. Do I still have a dual correspondence in the mirror? I should have. But what would that be? It's not the original me anymore. It is equal to the bra times the adjoint of raising my left hand. So if you look at the mirror, I raise my left hand. Actually, the image raised his right hand, right, in some sense, right? So it's just like you do not multiply the matrix to the vector, you multiply the adjoint of the vector, of the matrix. So this is a way to memorize, right? Now, why multiply from the right? Think about it. Alpha times x hat. Alpha is a row or column vector now in the bra. It's a row or column. I mean, what I'm saying is this. I should say alpha bra. Is it a row or column vector? Row. Why? Because it's bra. Because we transpose it and then we take the complex conjugate, right? That's how you get it, right? This one you really need to be very familiar with this. So this is something like this. So as a result, you need to multiply it from the right. Otherwise, you cannot multiply. Try to multiply a matrix to a row vector. It doesn't work, right? The row times the column, right? It doesn't work. But now this works because the row times column, row times column, row times column give you another row vector. But so this is a must, right? Even you forgot the direction, then you try to write down the matrix multiplication, you find that it doesn't work. So this is a rule. No one proved this. This is the definition. Kind of like definition, right? And it works out correctly, right? Okay, any questions? Now this one is not that important if x matrix times a vector equals to another matrix times a vector for any vector. So I do something to all the vector, it all give me the same result as the other vector, the other matrix to do those vector, then these two operations must be the same. Okay, you just think about rotation. If I apply a matrix to rotate a certain vector, and it is equal to another matrix that I used to rotate this vector. If for every vector they are the same, then both rotation must be the same. Okay. And also, there's something called null operator. If that x times a vector become a zero vector, look at this. This is a zero vector. It's not zero scalar. It's just that every entry here is zero. So this is not normalized. You should not see this in quantum computing, right? Because it doesn't have a unit length, right? But however, just know this, right? So naturally, here, if I have a matrix, let me ask you one more time. What is alpha cat? Is it a vector, scale? Maybe I need to pick person, right? Maybe what is alpha? Is a vector, scalar, or a matrix? Vector. Column vector, even better, right? But in our class, all the cat will be column. Yeah, but column vector, not bra. Very good, right? Who want to answer? How about C alpha? What is that? Is that a vector or scalar? C alpha. I did not tell you actually, but it's. Can you guess what is C alpha and C beta? Scalar. Very good. Then what is scalar times a vector? Vector. You just times number, right? Then what is vector plus vector? Still vector, right? Then what is matrix times the vector? Like what we're saying. It's just like this alpha becomes so complicated, but still a vector, right? So if the whole thing is a vector, I should have a dual correspondence on the right. A cat version, a bra version, right? So what is that version? Of course, you can do the multiplication, find the matrix, and then do the transformation. But you can also say that, first, I must have my bra version here, just like my image. Just myself and my friend add together, stand in front of the mirror, is equals to my image in the mirror and my friends in the mirror standing together. However, we've done some scaling. The scaling is like I need to multiply the complex number of them. And then we both rotate 90 degrees in the real space, in the real world. It's equivalent to they rotate 90 degrees, we rotate to the left equals to the mirror image rotate 90 degrees to the right. which is X dagger. Like analogy. Do you see this? Yeah. So here, this equation is the same as this one in some sense, because again, it's a matrix times vector correspond to the bra version of the vector times the self-adjoint of the matrix. Okay, so this need to be very clear. Now here is a typo, right? I want to see if you can find it, but anyway, now associate property. This is very important. I have beta x alpha. Okay, a little bit complex. Do you know what is this? Someone guess. Who think this is a vector? The whole thing. Okay, someone thinks yes. How about who think it is a matrix? Who think it is a scalar? Only a few think that, right? Can we break it down? I mean, the whole thing, it only can be one, right? What is alpha? It's a column vector. So I'm very happy that he's very specific, so cannot be wrong. Column vector. What is x times alpha? Vector, column vector, because it's matrix times column vector, right? Then this is a vector doing inner product with beta, which is a bra. You can think in this way. This is a vector. Column vector times the row vector. So what is this? Inner products give us what? Scalar. That's why it is scalar. Right? So you can look at this in different things. Now, how about look at this? You can group them. That's the associate property. I can play with this first. Beta is a bra, row vector. Multiply to a matrix, right? This matrix doesn't matter. Do not think that you need to be labeled as adjoint. It's just a matrix, right? In multiple to a matrix, what is that? A bra times a matrix is what? Still a bra itself. So the row vector times a matrix is still a row vector. And then a bra times the cat is again the inner product. So again, this is scalar, right? So this equation just tells you that if you see something like this, this is a very important expression you use to find the expectation value. Hadamard test, we did not do this in this class, but this is very important. Eventually, no matter what you do in the real space in experiment, you want to get a number, right? And you put this expectation value. So here just saying that if you see this, feel free to opt to calculate this first, beta times x or x times alpha first, and then do the second step. That is what it is talking about here. Okay, then from here, we derive another important equation. If you remember, A inner product with B, this is the inner products, right? Correct? It is equal to B inner product with A, but with the star. Complex conjugate, thank you. Because this is a number, right? A complex number, right? If I swap it, then I just put a complex conjugate, then they will be the same. Right? This was what we learned in the last two lectures ago. Right? This is something you need to memorize or put in your cheat sheet. Now then, how about for this one? I have beta x alpha. I can treat this whole thing as a bra, right? I just said that it's a bra times cat, or inner product of this vector, whole vector, beta x times alpha. So I can use this equation. I can put alpha, make it as a bra this time. And then make this one, find the cat version. I should say this. I find the bra version of bx times the cat version of alpha equals the bra version of alpha times the cat version of bx. Right, just like here, bra version of A times cat version of B equals to the bra version of B times cat version of A, complex conjugate. So here I have bra version of this thing, it becomes the cat version, and then the cat version of this becomes the bra version, right? So I just write this alpha, x star beta, and then add this complex conjugate, they should be the same. The only confusing part is why this bra version of this when it becomes the cat, it becomes this, is because of this formula, right? Because I have bra times matrix, then its cat version is the complex conjugate of this matrix times the cat version. Okay, so this one may be, you get confused because I don't have a dagger here, but it doesn't matter because if, by the way, did I teach you this? What is x dagger if I do it 2 times? Right? As I told you earlier, it's similar to complex number. What is the complex conjugate? You take it 2 times for a complex number itself, right? Same here is x, you're right. Because you do the transpose and then do one more time, row become column, and now the column becomes row again. And then the complex conjugate, you take it 2 times, right? So it equals to itself. So this one I can safely write it as is the same. I can say this one is x dagger alpha correspond to alpha x dagger, right? I can just, it's a little bit messy. I don't want to keep it here, otherwise difficult to study, right? So that's why I have this. Now, based on this, then it means beta x alpha equals to, here is the typo I have. Can you tell me what typo, what mistake I make here? I'm saying based on these 2 equations, it just come here directly, right? So what is the mistake? Yeah, please. It should be have dagger is here. Yes. Correct. I need to swap beta and alpha. Say again. We define what? No, a scalar x is the matrix. Did I confuse you that it is scalar? X is a matrix in this whole slide so far. C alpha, C beta are the scalar. Is this okay? I think I used too much time, but still good. Yeah, is that okay? Okay, then we have this summary, right? So you can take a look. Now this is the last important slide of this lecture. Why we want Hermitian matrix? Because their eigenvalue are real. And eigenvalue are something you're going to measure experimentally. And you need to have something real. Otherwise, it's impossible, right? You find out what's the velocity. You cannot say the velocity is 1 plus 2i meter per second, I mean, right? So Hermitian matrix, or all our observable, must be correspond to Hermitian matrix. Okay? So here I will just go through the proof. If A equal to A dagger, means it is Hermitian, right? Our definition. Its eigenvalues are real. So here is how we prove it. First, we let the eigenvalue be lambda I, and the eigenvector be cat lambda I. This is okay? Again, I can put anything here. I can say the eigenvector that has the eigenvalue lambda I, but now I just put lambda I. You understand this is just a description. It's referring to a vector that has an eigenvalue lambda I. So by definition, the matrix times the vector equal a number times the vector itself, then lambda I is its eigenvalue, and lambda I in this cat is the eigenvector. Is this okay? They need to memorize the definition of eigenvalue and eigenvector, right? So now my goal is to prove that lambda I is real. Here I just expand it, right? just in writing. A times eigenvector corresponding to eigenvalue lambda I equal to lambda I times eigenvector corresponding to eigenvalue lambda I. Right. So how do I prove it? I do this one. Right now you should be more familiar with this notation. You can do the first part first or the second part. But after all, this is a bra of lambda I times a matrix times the ket of lambda I. Now, I do the second part first. What is A times lambda I? Based on I just told you. A times lambda I equals to lambda I times lambda I ket. Because this is its eigenvector. That's why I put lambda I here. Now, this is what? A scalar. Right? So if it's a scalar, now think about matrix. I multiply a scalar in the middle. I can take it out. Then it becomes the inner product of lambda I. Because I take out lambda I, right? This is a number. What is the inner product of the lambda I? I actually should have said that I assume that it is normalized, orthogonal. Okay, I assume it is normalized. Maybe I should say that. I did not say that here. Right. Assume normalized. Maybe I don't need to assume normalized. I mean, if I keep it, I will get the same results. But here, for simplicity of proof, I assume it is normalized. I don't need to assume it's normalized. Okay? Correct. Just the magnitude, right? It becomes, it must be a real number, right? So very good. But to make this simple, I just assume it is normalized. But you don't need to be normalized to prove that it is real. Is that okay? And that's why I just make this equal to 1. Okay? Now, so it means that this expression equals to lambda I. Okay? Now, then I apply the star to this expression. Right? I'm allowed to do that, right? I just apply. I'm not saying it's equal to whatever. If I apply star to, complex conjugate to this, I need to apply the complex conjugate to lambda I also, right? Make sense? Just two sides, because this equals to this, then the complex conjugate of this must be equal to complex conjugate of this. Okay? Now, but then, in the last slide, I just show you that over here, I can swap them and apply a complex conjugate and make the matrix self-adjoint, right? So that is what I'm doing. I swap them, but because these two are the same, so it's still lambda I. But the A becomes A dagger. But I need to add one more complex conjugate, so I have 2 now. On the right-hand side, it is still lambda I star. So from here to here, do you see what happened? I try to swap them and then make A the dagger. Right? Here I swap A and B and then make the matrix dagger adjoint. But I need to add a complex conjugate, then they are still the same. I basically saying for this expression, I swap them, I find the adjoint of the matrix, and then I apply a complex number to it, then it will still be the same. Okay, 3 steps. Swap, find the adjoint, applies complex conjugate, then you are still the same. This is what I'm doing. Swap, no change for swap because both are lambda I. Make A dagger, self-adjoint, apply one more complex conjugate to the whole thing, then this should be equal to this, right? And this is still equal to this. But if you take 2 complex conjugate, then this is gone. And remember, this is Hermitian, so A equal to A dagger. So I again can write this one as A. Right? And this one doesn't change. So basically, I'm saying that this expression, which is the same as this one, equals to lambda I star. It also equals to lambda I. Then it means what? lambda I equal to lambda I star, something equal to its own complex conjugate, then that thing must be real. That's what I want to say. I will continue because, sorry, I spent too much time. I will continue to talk about the homework. Right? I know it's 5:45. But any question about this? Yeah.
Just review slide 789.
789. This is the last one. Yeah. Any question about this process? But I really want you to go back to follow, right? If you cannot follow now or any doubt. But ask now. Don't wait if you can. Okay, if no, let's take a look at the homework, right? So, how to do this? Sorry, my homework is pretty intensive. You need to write a lot. You can use MATLAB. I think it's okay if you want to do that, but the best is you try to write out, because I hope that you can go through the process one time at least, right? What's the pen? Yeah. So the first question is that you are given 4 bases. They are called Bell bases, right? We will learn that later. Now, I jump directly to C4 space, okay? Although I did not tell you what is C4 yet, doesn't matter. You see that it has 4 basis vectors. So what is the dimension of this space? It has 4 basis vectors. Huh? What is the dimension of this space? Huh? 4. Yeah. How many qubits does it have, do you think? For 1 qubit, we have 2 basis states. For 2 qubit, what do you think? We have not went into this detail, but go on. No. Now we have 4 basis states. 4 basis states. Yes. Right? I don't want to difficult write. You have 2 qubits. 1 qubit gives you 2 basis states, right? 2 qubit, you get 4. 2 times 2. Right? It will go exponentially. That's why quantum computing is so powerful. Right? But remember at the introduction, I talked about that, but doesn't matter if you are not aware of that, we will talk about that later. But basically what I'm asking you to do is very simple. You don't need to understand all this. First, you show that they are orthonormal. By definition, what is orthonormal? Delta Ij, not delta Ij, sorry. I mean vector I, inner product of vector I and vector j equals to delta Ij, right? If I is not equal to j, then get 0, right? So this is one of them. This is I. Maybe let's call it I equal to 1, right? If you want to label them, this is I equal to 2, I equal to 3, right? I equal to 4, or you start with I equal to 0. But basically here is to show that they are orthonormal, so you need to form the inner product, right? How do you form the inner product? Define the cat version of this one, the bra version. Can you give me an example? What is the bra version of this one? Here I did not write it as a cat, but it's okay. I give you a column form. It's the cat, right? It becomes 1 square root 2, 1, 0, 0, 1. Are you guys okay with this? And then do the inner product, right? Do the inner product to itself, do the inner product to others. If you want to show this is orthonormal, you need to do all of them. So 16 operation, but they're all 1 and 0. You will see that easily. Just show me. I want to go through one time. Is that okay? And then you can have another basis set for the same space. And we say we can use this. U1, U2, U3, U4. This is another basis state, right? I just want you to express each of them. For example, U1 in terms of the linear combination of the Bell state. You see, U1 is 1, 0, 0, 0. Basically, you by looking at the top, you see that if you addition, for example, I see that this is what? 5 plus 5 minus will give me something that 2, 0, 0, 0, right? Do you see this? I don't have the pointer. Right? Add this to this, correct? You add the first two together, you become 2, 0, 0, 0, correct? Yeah? Then you do something, right? I only give you this one, then I just asked for linear combination. I did not say that you can only add them. You can have coefficient in front so that you get to the right result. So are you okay with this adding together become 2, 0, 0, 0? Okay, you agree, good, yeah.
So hypothetically, you don't necessarily have to worry about the coefficient. It's still on the same lines. You're just once stretched out.
Yes, but I still need you to worry here because we need a normalized vector. So, but you're okay with 5 plus 5 minus become 2, 0, 0, 0, right? Okay, let's do this here. It's getting messy, right? Let me do it here. I'm recording, yes. What is this? What is this? Can you tell me? Let's do substitution. What is 5 plus? What is 5 plus? 1 over root 2. Yeah, I'm recording. Feel free to leave. And then what is 5 minus? Thank you. You add them, what do you get? Are you okay with this, all of this, all everyone? Right, but I put, yes, I have not, yes, correct. But for this, are you okay? But I want to get, like what he said, this is root 2 times 1, 0, 0, 0, right? Correct? You take the 2 out. 2 divided by root 2 becomes root 2. Yeah? So I don't want to get this, so what should I do in the linear combination? Well, I can say that this equal to 1 over root 2 of this one plus 1 over root 2 of this one. Then I have an extra 1 over root 2 here. Another 1 over root 2 here, right? Then this one give me 1, 0, 0, 0. So when I'm writing this is the answer. So I gave you the answer already. U1 equal to 1 over root 2 times 5 plus 1 over root 2 times 5 minus. Oh, it's difficult to see, right, the green.
Yeah, I think the course.
Yeah. But do you follow? I know it's too bright, yeah. Okay. So this can be done easily by observation. So we have not learned the equation, but we just do the observation. You can do that, right? Now, this part you are not ready yet. We will do it on Wednesday. I will give you a transformation matrix. So instead, by looking at this by observation, we will learn that in order to rotate it, so let me just erase all of them. Right, we will learn on Wednesday. You need to watch the video. How to do the transformation. So what I just showed you that is you by observation, you show that U1 equals to 1 over square root 2 psi plus psi minus, right? This is by observation. But we can also find a matrix that tell us that, oh, I forgot part C, I'm sorry. I'm talking about part D already, right? Then later, sorry. I need to finish part C first. So first for U, right? This is U, this is given. I want you to just use observation. U equals to A times U1 plus B times U2 plus C times U3 plus D times U4. Can you do that? Should not be difficult, right? This one. Now, just by observation, you just ask how U1, U2, U3, and U4 add together will give me U. It's just a linear combination of the bases. Like I give you a 45-degree vector, you say it is x hat plus y hat. Any questions? And then for D is that instead of going through this, we actually have a matrix to help you to do the transformation. So here, actually, I also overlooked C has two parts. First, linear combination of U1 to U4. Another is linear combination of the Bell bases. So you need to first find out U in terms of U1, U2, U3, U4. And at the same time, also find out U in terms of the Bell bases here. Phi plus phi minus psi plus psi minus. And you can use substitution to find that. Right? So since this is easy, let me just tell, I mean, not easy. The first part is straightforward. Can I just say that U equals to 1/2 times U1 plus U2 plus U3 plus U4. Do you agree with what I said? This one is the basic. U equal to this. Do you agree? Yeah? And then you already find out what U in terms of the side bases are, right, from part B. Then you just do substitution. Just now we say U1 equals to 1 over square root 2 psi plus, phi plus phi minus. We just say that, right? You just substitute this to U1 and do the same thing for U2, U3, and U4. Then you are expressing U in terms of the Bell basis already, right? But this is troublesome. That's why I asked you in part B, use the transformation matrix that I will teach on Wednesday. Okay. The last one, I don't want to tell you anything. Go back to where we discussed about the Heisenberg uncertainty principle for the simple case. You can say something similar here. It is very simple, just a few statements will be done. Okay? Question 2 is just purely a practice of inner product and also how to find the magnitude of the inner product. This gives you the scalar, but it's a complex number. Then you need to find the magnitude of the complex number, right? Which is the real part square plus the imaginary part square and take the square root. Okay, just a practice. Now here is about the eigenvalue. We spent a lot of time last time to find the eigenvalue. On Wednesday, we will use another method to find the eigenvalue. So you decide to use which method, right? But actually, the first one I asked you to use the slide 4 from lecture 5, which is the, I think it's the it's just by solving the equation, right? To find the eigenvalue and eigenvector of I, or of sigma y. And then here is to find the eigenvalue of sigma x using the determinants method on Wednesday. Okay? And Q3 and Q4 must be the same. Now, here actually is I just want you to repeat what I just showed today in the slide. Prove that the Hermitian matrix has real eigenvalues. You just repeat. I want you to really be clear of what you are doing, how to prove that, right? Every step needs to be clear, right? No hand waving, don't jump. Explain clearly why you can go from this step to another step, okay? Now then, we have learned the spin matrix in the arbitrary direction, which is n dot sigma. Maybe you forgot already. In any direction, you have x, y. The spin matrix corresponds to a magnetic field, maybe in this direction, right? Is what? Equals to the unit vector dot product with sigma. I deliberately don't want to say now. You just check the natural note. I clearly say what is sigma x, right? Is the vector a linear combination of sigma x, sigma y, sigma z. I want you to prove that it is Hermitian. What does it mean? I want you to prove that n dot this one equals to n dot this one dagger. And we already show what is n dot sigma in matrix form in the slide. Take a look. I want you to spend time to look at the lecture notes. Okay. And then you want to find the eigenvalue again through the tedious way, but I want you to guess what should be the eigenvalue first. Because the spin matrix is corresponds to the observable of the spin we have in the space, right? And I already told you that sigma z and sigma s, or even sigma y, both have, you will find that in question 3, they both have plus minus 1 as their eigenvalue. So I think you already can guess why. And that's what we have been talking about, right? The universe is isotropic. Question 7 for arbitrary, this is just arbitrary vector, 2 qubit, spin up, spin down, right? And we say if the eigenvalue of spin down is negative and this is spin up, then what is the FH value when measuring the spin in the z direction? Now this one will, this is just a regular question. When you do a measurement on the arbitrary state, what will you get? I try to measure whether it's spin or spin down. What happened to the wave function when you measure it? Collapses. Collapses to what? Very good, either up or down. But what is the probability of getting up? Here is b, yeah, equals to b squared. And the probability of getting down is s squared, right? And then how do you find the FH value of a measurement? You find the probability of getting down times the value, which is -1, plus the probability of getting up times the value you will measure, which is +1. That gives you the FH value, right? That is the definition of probability. Think about that, right? You do an experiment. You can get this value. Each has this probability. And that is how you get it, right? Make sense? Like gambling, right? You say I have a 30% chance of earning $100 and then 70% chance of earning $200. What is the FH return? 0.3 times 100 plus 0.7 times 200. That is my FH return. Right? So nothing special. Now, then I want you to go through this matrix multiplication. Look at this. And you will find that this one gives you the same result. That is how you find the expectation value. Right? We will teach that later, but now you can use this to find already. And what is the meaning of this expression? We just explain in detail, right? It is what? The bra of psi times sigma c times the ket of psi. Right? By the way, how do you write the bra of the ket of psi in this case? How do you write it? It's a column vector or row vector for psi. This is psi. Yeah. Now here I have a trick here, right? Which is okay. If you put z in this form, then this one will correspond to down, and this will correspond to up. Okay? So how do you write it? This is B, this is A. What is the bra version of this vector? Is it row or column? How do you write this one? Is it row or column? For this one, bra, is it a row vector or a column vector? This is a row column vector, right? Then what is, this is the column vector. It's a row vector, right? So what is the value here? How should I put this is a row vector? What's the entry? He said BA, is that just BA? How do we form the bra of a cat with the conjugate? Okay, so we really need to look at the slide carefully. But you only need to make mistake one time, then you memorize for the rest of your life. So really be careful, refer to the slide. And then you do the matrix multiplication, right? Now this one is nothing special. Here say, we give you a squared plus b squared equal to 1, show that this is unitary. You don't know what is unitary, we'll cover on Wednesday. After that, you just prove the definition. But I can tell you now, it means u dagger times u equal to I. Hermitian is a equals to a dagger. Here is u dagger times u equal to I, okay? Number 9 is, again, just try to waste your time to go through the matrix multiplication, okay? So we define a new matrix, which is a tensor product of this. We will learn tensor product almost on Monday, so maybe that is almost the due day, right? Actually need to, 17 is Friday? No. Oh, no, I think I need to extend it maybe by a week. That would be better, so that you learn this tensor product first. Okay? Yeah, maybe I put it wrong. Yeah, express in matrix form, show that they anti-commute. Just follow the definition, yeah.
So for this one, that's just
It means the identity matrix of the second qubit.
okay.
Yeah, yes. So let me extend it to 5. So any questions? Please ask now. If not, I will stop here. Okay. Yeah, do try to think. I want you to go deep. Okay.